So welcome back to all. So this is the 18th lecture of quantum mechanics, and this lecture is about the Dirac notation and orthogonality. Okay, so previously whatever the integral that we have written is always a time consuming to write those integral equations. So to make our life much more easier, there is some type of shorthand representation of these types of integral equation, which is known as Dirac's notation. So here in this slide we will see that how these types of Dirac notation can be written. So suppose that psi is a wave function which is a basically function of x, n is the quantum number of this wave function psi. So this wave function can be represented by the Dirac notation, which is this one, where a dash, then the quantum number n, and then there is a signature of greater than, and the whole thing is called the Ket vector. So by using this Ket vector we can represent this wave function psi nx. Similarly, the complex conjugate of wave function psi m can be represented by another representation which is called bra vector, where instead of writing greater than sign, we can write the lesser than sign, then the corresponding the number m, and then the dash, and the whole signature is called the bra vector, and they both together form the bracket vector notation. Okay, so suppose that we have some integral minus infinite to plus infinity psi m star x psi n x dx. So this is the whole integral. So we can write this integral using Dirac notation, which will be like this bra vector, then m dash n, and then this Ket vector. So you can see that how much simplified this thing become after using the Dirac notation. So we can save lots of time as well as space while writing these types of big integral equation, because we have to often encounter these types of big integral equations in quantum mechanics. So these types of Dirac notation will save lot of our time as well as efforts. So generally in my previous lecture I have given a brief description that how we can express the expectation value of some observable. The expectation value of any observable a can be expressed by this integral, where this is minus infinite to plus infinite psi m star x. A is the corresponding operator operating on the wave function psi nx. So this whole integral can be written in form of Dirac notation, that is equal to this one, where this is the less than sign, then the m, then dash a n, then greater than sign. So this whole integral equation, that is the expectation value of a, can be represented by this small formula or this small equation, which is known as Dirac notation. So similarly, the normalization integral, when we have to write the normalization integral, we have seen that instead of this a operator, only the integral will be equal to minus infinite to plus infinite psi m star x into psi nx dx. So this can be this normalization integral can be written by this form, and this is equal to 1 if the wave function is normalized. So all those things you already knew. Now if the wave function is not normalized, then the expectation value can be represented by this one, where this is the expectation value when it is fully normalized. But if it is not normalized, then we have to introduce the normalization integral in the parenthesis of this equation. So you can see that how we can represent the big integral equation into a small equation, which is known as Dirac notation, which will save lots of our efforts as well as time. Now another important thing to be mentioned in Dirac notation that for any operator to be a Hermitian operator, there is some condition that the expectation value of the corresponding observable A will be equal to the expectation value of its complex conjugate. So this is the criteria that has to be satisfied if the operator has to be a Hermitian operator. So we can see here that the expectation value of A can be represented by the Dirac notation M A N. So this has to be equal to this A star, which this can be expressed as M A star, that is complex conjugate of A operating on N. So we can write this Dirac notation or we can rearrange this Dirac notation into this form, where we can take this N in this place. So this will become the N star, and if we take this into this side, right side, M into this side, this is become only M, and if you put star on the whole equation, then it is equal to this one. So if the operator A has to be Hermitian, this equation has to be satisfied, where M A, this operator operating on N, has to be equal to N A operator operating on M, and it is the complex we have to take the complex conjugate of this whole notation. So this condition has to be satisfied for any Hermitian operator. So it is better that you should memorize this equation, and because this equation we will use in many portion of this quantum mechanics lecture, so it is better that you should understand that why this equation, why the condition is this one, and you have to memorize the condition for an operator to be a Hermitian operator, and this is the condition. Okay, now I will talk about the concept of orthogonality. So what is orthogonal? Orthogonal, we can say that suppose we have three coordinates like x coordinate, z coordinates and y coordinate. So the unit vector along each of these coordinate x, y, z are orthogonal to each other. Why they are orthogonal to each other? Because if we change any value along the x axis, this will not affect the z value or y value. So the value any changes along x axis will not affect the y value or z value. So that's why we say that x, y, z are mutually orthogonal to each other, because they are not affected by each other. So that's why they are called mutually orthogonal. So there is some condition that two wave function, if this two wave function has to be an orthogonal to each other, then the condition for orthogonality is this one, where the integral minus infinite to plus infinite psi m star x psi n x dx, or we can represent this integral by Dirac notation using this. If it is equal to 0, then we can say that psi m and psi n, these two wave function are mutually orthogonal to each other. Now in my previous slide I have talked that the expression of the expectation integral or the expectation value of any quantity or observable can be represented by this integral, which can be represented by shorthand Dirac notation MAN. This is called the expectation integral. Now if psi m and psi n are orthogonal to each other, and psi n wave function is an eigen function of the operator A, then this expectation integral will be equal to 0. So how this is possible, that I will describe here. Now if psi n is an eigen function of the operator A, then if we operate operator A psi n, we will obtain an eigenvalue an into the same wave function psi n, because psi n is an eigen function of the operator A. Or by using Dirac notation, we can write this A operating on the wave function n, that is equal to an into this wave function psi n. Okay, now coming back to the expectation integral, which is m, then wave function psi m, a operator operating on the wave function n. Now this a operator operating on wave function n, and as this psi n wave function is an eigenfunction of the operator a, so we will obtain an into psi n wave function. Now an, it is called an eigenvalue, so this will be out of that integral, so it will become an m psi m star into psi n. So as we have discussed that if psi m and psi n are orthogonal to each other, then this integral, that is called the overlapping integral, will be equal to 0. So you can see that the expression of the expectation value of a, that is also will be equal to 0 if psi m and psi n are orthogonal and psi n wave function is an eigenfunction of the operator a. Now suppose a is an operator which is a linear operator. So what is a linear operator, that I have already discussed in my previous lecture. So if you have any doubt regarding this linear operator, you can go back to my previous lecture. And a is also linear as well as Hermitian operator. That is the assumption that we will take. Now we will prove that if a operator is a linear as well as Hermitian operator, then the eigenfunction of this operator will be orthogonal. So this thing we will prove in this slide, that the eigenfunction of any operator which is linear as well as Hermitian will be orthogonal. So suppose that psi m and psi n, these are the eigenfunction of this operator, and this operator is linear as well as Hermitian operator. Okay, so if it is an eigenfunction of the operator a, then a operator operating on psi m wave function will give the eigenfunction am into psi m. Similarly, this a operator operating on the wave function psi n will give the eigenvalue an into the same wave function psi n. So this condition has to be maintained if this psi m and psi n wave function are the eigenfunction of the operator a. Now again I have told you that a is a Hermitian operator. So for an Hermitian operator, this equation has to be satisfied, which I have discussed in my previous slides, that if a is a Hermitian operator, then this condition has to be satisfied. So we will use this criteria for an operator to be a Hermitian, where psi m wave function, then a operator operating on psi n will be equal to psi n star wave function, a operator operating on psi m, and it's equal, and this will be equal to its the complex conjugate of this integral. Okay, so let's look what will be the value of this integral. So a operator operating on psi n wave function, and as psi n is an eigenfunction of the a operator a, so we can write that psi m wave function, then the eigenvalue an into psi n. So this is the eigenvalue, and this will be out of this equation, out of that integral. So we will obtain an psi m star into psi n. So this overlap integral we will obtain. Now what will be the expression of this integral in a m star? So you can see that a operator operating on psi m will give a m eigenvalue and the psi m wave function. And if we take the complex conjugate of this whole integral, then if a m will came out of this integral, it become a m star, and the equation that we obtain is n m. Okay, so we can write this as a m star m into n. So there will be a star in this integral, so this can be expressed as a m star m n. Okay, so you can see that in my previous lecture I have told that the eigenvalue of any Hermitian operator will be real one. So this is the criteria for an operator to be a Hermitian. So this is the eigenvalue of this Hermitian operator a, so it has to be a real. So the criteria for an any number to be real is that it has to be the equal to its complex conjugate. So if it is am is a real number, then am will be equal to its complex conjugate am star. So we can write am instead of am star. So we can write this am and this overlapping integral. Okay, now this and these two equations are equal. So equating these two equations, we will obtain an, this overlapping integral will be equal to am into this overlapping integral. So these two are same, so we can take this into left side, and rearranging this equation we will obtain an minus am into this overlapping integral, that is equal to 0. So this equation will be true if an and am are not equal to same, or we can say that if the eigenvalues are not same, or if they are non-degenerate, then this integral, this overlap integral will be equal to 0, which means that the wave function psi m and psi n are orthogonal to each other. So this condition is satisfied if am and an are non-degenerate, or they are not equal to 0, and the operator A is a linear as well as Hermitian operator. In that case, the eigenfunction of this operator psi m and psi n are orthogonal to each other, because their overlapping integral is equal to 0. So up to this, if you have any questions or doubts regarding this lecture, you can ask me through the comment section. I will try to resolve all your problem. And do subscribe to my channel, that is called Chembiosis, and this channel is basically meant for graduate student of chemistry. In the next lecture I will talk about the superposition principle of quantum mechanics. So I hope that you have understand this lecture, and thanks for watching my lecture. Thank you.